Well, greetings, everyone. It's time for our September meeting of New Mexicans for Science and Reason. I'm Dave Thomas. We've got our Vice President, John Covan, in the Zoom room. And tonight's speaker is Trish Henning. I just looked it up. This is actually her fourth talk for NMSR all the way back to 2002. And most recently in 2016 on Hidden Galaxies. So it's been about 8 years, but we are delighted to have her back. Got a little announcement before we get rolling, and that is our next meeting is going to be a little early, October 9th, so a little less than a month. Because the following week is our big alumni get together at New Mexico Tech, and our band is playing, and so it's a very busy week. So, but on October 9th, David Weinberg, who just logged in, is going to be talking on curing all diseases again, trampling scientific boundaries for fun and profit. So we're certainly looking forward to that. So without further ado, I'd like to introduce Dr. Trish Henning. Are you still at UNM?
I'm not, Dave. I'm at NRAO. I'm at the VLA.
Okay, and how long have you been there?
I've worked for NRAO for 4 years
Okay.
now, but I've been director of the VLA for 3.
Excellent. All righty. So, so her topic is the very large array from the past to the next generation, and there is all kinds of new things happening with that. So I'm been very eager to hear what you've got. So without further ado, Trish Henning, thanks for coming.
Okay, thank you. Can I share my screen?
Yes, you can. Oh, let me anoint you with the speaker oil.
Uh,
So here we go. Uh, make a co-host. And there you go.
okay, let's see if I've clicked the right button now. Let's see. Let's do that one. Let's do that one. Let's start it.
Looking good.
Okay, let's do from the beginning. From the beginning. What are you seeing?
I see the VLA.
Oh, that's awesome. Okay, hey, okay.
It's looking good.
Well, okay. Thank you, Dave, for inviting me. I hadn't realized it was more than 2 decades, but sure, I guess it time flies when you're having fun. So
The most recent one was 2016.
yeah, okay. So it's been a little while. Yeah, I've had a bit of a shift since then. So
Yes.
thanks for the invitation. Yeah. No, so what I want to talk about today is the very large array. Now, of course, we're all on Zoom, so I don't know where you are scattered since we're not in the same physical room, but I'm thinking that it's quite possible that some of you have gone out to see the VLA. Yep, thank you. I see some hands. That's great. But what I'd like to talk about tonight is talk about the VLA, give you an update on what it's doing, because it's still doing very cool science, even though it's over 40 years old. But I do want to talk about our plans, which are actually happening. Interesting things are happening out at the site for plans for the next generation VLA. So let me just start, because I know we are a science group, but maybe with different kinds of backgrounds. So what I want to talk about tonight, really what I'm talking about, is telescopes and what they can tell us, and in particular, radio telescopes. So I want to talk a bit about what it is that we're actually measuring. What are we actually observing in the sky? And just this is quite likely familiar to folks, but just a reminder that objects in the universe, stars, galaxies, hot gas around black holes, all kinds of planets, give off naturally, they give off electromagnetic radiation. Now we're most familiar with visible light, of course. That's a portion of the electromagnetic spectrum. And so what I'm showing you here is a electromagnetic spectrum visible in the middle. You can see the rainbow, which is really a measure of the wavelength of the light, with red wavelength, red light being longer wavelength, blue shorter wavelength. But there is much more to the electromagnetic spectrum than that. At shorter wavelengths, we get into the ultraviolet and then the X-ray and the gamma ray. At longer wavelengths, infrared and then microwave and radio. But it's all the same stuff. It's all the same radiation that we're looking at. And we learn a lot about the universe by using all of the different wavelengths. And so we build telescopes that are able to detect this energy over the whole spectrum. So we've got a picture here showing you telescopes that work at the visible. You see them in an artist's conception here, sitting on the surface of the Earth, and radio telescopes can sit on the surface of the Earth. But the atmosphere blocks radiation for the other wave bands, gamma ray, X-ray, ultraviolet to a large, well, to ultraviolet and microwave some as well. And that's good. We don't want all the gamma rays and X-rays and all the ultraviolet getting down to us anyway. So that would not be a good thing. But we can detect the radio waves, and you'll notice on this NASA graphic here, they've selected the VLA to represent radio telescopes. So does it really make that much difference what wave band we're using or what part of the electromagnetic spectrum we're looking at? And here's an example that I think is pretty compelling. So what you're looking at here, this is a visible light image of a very large galaxy in the Hercules cluster. It's a super giant elliptical galaxy, and this is with the Hubble Space Telescope. This is what it looks like. And what you're looking at here, what I'm focusing on here is the fuzzy patch in the middle. That's the very large elliptical galaxies, lots and lots of kind of old stars. And so you're seeing predominantly the light of old stars there. When you turn the VLA on this and look at it, this is what it looks like. So it's an enormously different picture of what's happening with this source. And what we're looking at here, the narrow features that come out from the middle of this galaxy. And I suppose I should ask, can you see my cursor?
Yeah.
Cool. Okay. Yeah. Nice. Okay. So yes, here's the fuzzy patch with Hubble Space Telescope. That's a lot of stars. The radio is these narrow features that terminate in these enormous blobs, and they are enormous. And you would have no sense of that from the optical image, but you get a very different picture. And what we're looking at is entirely different physics. There's a supermassive black hole down in the center of this galaxy, and two narrow relativistic jets going off to either side that terminate in the intercluster medium here, and very, very different. So this is a really, truly different picture. So let me talk a little bit about the VLA itself and where we are now. The VLA, we call it the VLA, and that's fine. Its full official name is the Carl G. Jansky Very Large Array, named after Carl Jansky, who was an electrical engineer at Bell Labs early part of last century, who first recognized radio emission coming from the sky. So we call him the discoverer or founder of radio astronomy. But what it is, it's funded by the National Science Foundation. 27 25-meter diameter antennas laid out in a Y shape, about 50 miles west of Socorro. I actually have 27 plus 1 here because there really are 28 dishes. We are constantly cycling them through one at a time for maintenance and overhaul. So you see the VLA dishes pretty close together here, one in the barn. So the one here in this big garage basically is having maintenance happen. And then the antennas are movable. So when we're observing, the antennas don't move. We park them on pedestals and they are stationary. But every 4 months or so, we move them along a rail system. There's rail lines that go along parallel to the 3 arms, and they are moved with a very special transporter. You can see this red thing in the middle picture here is our unique transporter that moves these 240-ton antennas along. The transporter itself, 90 tons, and it's quite something. We're just wrapping up a reconfiguration now. And so we move them to make a telescope of different effective sizes. So let's talk about that next. What these different configurations are and why we do that. Okay, so I'm showing a picture here. So I've got on the left in the smaller box here, the image shows the VLA in its smallest configuration. And if you look at this Google Maps on the right here, this picture of the sky centered at the VLA, these white circles, hopefully you can see those. When the VLA is in its smallest configuration, it would fit in this smallest radius circle. And then the next largest in the next circle, and then next, and then the next. And then for sizes, for actual sizes, if we talk about the distance between, or the longest distance between any 2 antennas, here's what the sizes are. So that smallest configuration that we call D, the maximum separation between any 2 antennas is 1 kilometer. And then when we reconfigure to the next largest, which is called C, it's about 3 kilometers, B, 11 kilometers, and A, 36 kilometers. And then I also, on this little chart here, I've got the minimum spacing as well. And you'll notice that for C and D, they're pretty close together. There's a limit to how close we can get them together, right? We don't want to crash them into each other. So why do we do that? The reason we do that is the separation of the antennas gives us the resolution of the telescope. Because each, and I'll talk about this when I show a picture of each dish in a second, or one of the dishes in a second, but each antenna receives radio waves, and we compare the signals from each pair of antennas. And so the farther apart the antennas are, the sharper the resolution, the smaller the angle on the sky it can resolve. So we call that the resolution. So we deal in angles. We don't know distances to objects when you're looking at them, right? When you look at the sky, it looks 2-dimensional, right? It looks like a big dome over your head. And so what you're really measuring is angles, not distances directly. And so the sharpness of the array, or the smallest angle it can resolve, depends on the separation between the antennas. Now, the largest, so A configuration, gives us the sharpest images. And by sharpness, I'm talking about, if you think, okay, 360 degrees in a circle, each degree divided up into 60 arc minutes, each arc minute divided up into 60 arc seconds. And the resolution does depend also on the wavelength that you're using. You get sharper images with shorter wavelengths. But basically, it leads to hundredths of an arc second at the shortest wavelengths and the biggest configurations, up to hundreds of arc seconds in the most compact configuration and longest wavelengths. So you might be wondering, well, why don't we always just want to be in the biggest configuration? Don't you always want the sharpest images, right? But we don't. If I can get that to advance, here we go. And here's an illustration of what happens at the different configurations. So this is actually that same radio galaxy that I showed a few slides ago. But that image that I showed before on top of the Hubble Space Telescope image was actually data from all 4 configurations added together. But now if we separate them out, look at one at a time, so I've got them labeled A, B, C, D. That's, remember, the A configuration is the biggest, the D configuration is the smallest. You see what happens. If you look at this galaxy in the A configuration, that top panel, you see the fine scale structure, right? You see that there's a little dot in the middle. You see, again, I've got my cursor. You see these very narrow jets coming out. There's the core of the thing. You see these nice skinny filaments, and you see this sort of turbulent tight structure. If you look at it in the B configuration, you still see some of that, right? But you start to see this more diffuse emission, and some of this fainter material gets clearer. And with the C configuration, you start to appreciate that these radio lobes are really enormous. So the thing with when you've got the telescope or the antenna spread very far away, you can't see the wide angle structure. You can't see the diffuse emission, right? Does that make sense? Are folks with me?
What frequency is this?
This one, that's a fantastic question. This is C and X band. This is like 4 and 9 gigahertz. Yeah. So astronomers write proposals for different configurations depending on the science they want to do, right? So it's a very flexible instrument, and so folks get to select what configuration they're interested in, what frequency they're interested in. And some astronomers want lots of frequencies added together. I'll show you some results from some other work.
Excuse me for interrupting. Do the different configurations use different frequencies?
No, they all have access to all frequencies.
Okay.
Yeah.
From 1 to 50.
That's correct. Yeah. So
okay.
that's exactly right. So let's talk about that. And another thing I should mention, let me go back one. I don't want, actually this will work. Okay. So here is the VLA and D configuration. And so you can measure, okay, here's the longest baseline. That's the widest separation of antennas. But you actually do get information on all the baselines. In fact, that's how we make the images, is that we use the information on each pair for each pair of antennas. And that's how we do that. We compare pairs of antennas in the imaging. And then the other thing to think about is if you're sitting on Hercules A, this radio galaxy, looking back on Earth, and the Earth is rotating beneath you, the array rotates. So the baselines change their angle compared to the object that you're looking at, and actually forms, ultimately, if you let it go, would form a circle, right? This as the Earth turns. And so we use that, astronomers can do what we call a snapshot, but typically they'll observe for some number of hours, and then the Earth rotates, and you get that all that information as you sweep out the baselines in time. Okay, cool. Yeah, so let's talk about those frequencies now. So I've added a point here: continuous frequency coverage from 1 to 50 gigahertz. So we got the 4 configurations, and then we have different receivers. We have 8 different receivers that cover seamlessly the 1 to 50 gigahertz. And the antennas, so an astronomer can ask for data at 1 gigahertz, 10 gigahertz, 50 gigahertz at any configuration. And I would comment, and this will lead up to, we're talking about the future. So the antennas themselves are getting pretty old. The VLA was commissioned in 1980. It's still doing great science, and a big reason for that is it had a large upgrade about 12 years ago that completed. So there was a major upgrade that finished in 2012, that increased the bandwidth of the receiving systems and got us that continuous frequency coverage from 1 to 50 in 8 different frequency bands. It also replaced, when I was a graduate student and first used the VLA, the voltage information from each antenna would come back to the control building in a evacuated waveguide in the ground, and now it's fiber optics. So it's fiber optic system, and also got a very much more powerful computer to correlate the data on the various baselines, and also improve the software systems and so on. So let's focus on one dish, and you can really see where these receivers are. So what we're looking at here on the left is one antenna. And so what happens is the radio waves come in, hit this primary surface, and bounce up to the subreflector. So radio light comes in from the sky, bounces off that large antenna surface and is focused, comes up to the reflector, and then is focused down on one of the 8 receivers. So now let's zoom in, looking at, here's the tops of the receivers in the green circle. We've got 8 cryogenically cooled receivers with mystifying names, LXCSKUKQKA. As you can see, they're labeled, but here's the L band receiver, here's the S band receiver, CX, and so on. And those just correspond to the different frequencies. So L band is 1 to 2 gigahertz, S band 2 to 4 gigahertz, C band is 4 to 8 gigahertz, and so on up to Q band, which is the highest frequency one. The numbers seem, or sorry, the letters seem random, and it's because they are. This is a system that dates back to World War II, when radio astronomy grew out of the technology of World War II, where the letters that it was used in radar and communications were meant to be confusing. So they don't mean anything. When I first started, I thought L was long. It's not. It's a random letter, just 1 to 2 gigahertz in here. So now that's the main workhorses, the 1 to 50 gigahertz. But up here encircled in red, I got this red arrow pointed to, it's actually at the subreflector. We have a couple of longer wavelength or lower frequency receivers, and they're hard to pick out, but there's a little tiny cross, a little dipole right here. And that's centered at about 340 megahertz. And then can you see this box, this square, I should say? This square structure, it's just wires, basically. That is a receiver that is sensitive to the longest wavelengths that we work with, which is down like 74 megahertz. And that doesn't get a letter. We call that 4-band. If I were still teaching, I'd ask, why do you think we call this 4-band? Because 74 megahertz is 4 meters. If you think of frequency times wavelength equals the speed of light. But okay. Okay, so the VLA, and people write proposals for any configuration, any frequency combinations. That's pretty common. People might want more than one frequency. They might want more than one configuration. So it does a whole lot of different kinds of science. And so let me just run through how do I organize this? Well, what I'm listing here is just all of the different categories that we receive proposals in. And so we've got different panels of astronomers who review the proposals, and to be fair, we want to compare apples to apples. So, kind of go gather up solar systems, stars, planetary systems, and, look at those all in one panel. Gravitational waves, energetic transients. I'll show you some transient results in a little bit. Pulsars, compact objects, star death, star formation, and so on. So it's a very flexible telescope that does all kinds of different science. Anybody on the planet can write a VLA proposal, and it will be entered into the competition. We get expert astronomers from all over the place to help us. They do the review and make a recommendation to us about what the best science is to get on the telescope. We get hundreds of proposals every year. And when proposals are selected to be on the telescope and get time, there's no charge to anybody to use it. That they will just do their observations. And it used to be when I was a student, you knew exactly when your observations were going to be. Now it's more efficient actually to do what we call dynamic scheduling. And so, it's not very romantic anymore. You get an email saying your observations happened and your data is ready. Come pick it up in the archive. But what I'd like to do is tell you about some recent highlights from the VLA. And again, there's just too many, hundreds of papers, hundreds of proposals. I can't do a complete survey, but there are some particularly cool results I'd like to tell you about in the last couple of years. And so let me start with one of these transient sources. In other words, something that was there, it wasn't there, and then is now, and then even may fade. So with the VLA, not just a few years ago, a new type of exploding star was discovered with its behavior. This was a predicted thing, but never seen before. So let me talk you through this. So if you look at the panel called A, this is a VLA survey that was done back, this one in 97. Yes, so this was back in 1997. This thing wasn't here. And then when the VLA looked again in 2017, here's this bright source. There is a galaxy it sits in. You can see where this source would be on C. And so what we think is going on here, what this is consistent with predictions, is this is a supernova. This is a star that exploded, which was most likely triggered by a collision with a neutron star or a compact object, another dead star that it ate, and then that was enough of a trigger to blow it up. So this is a merger-driven core collapse supernova. And so this shows you the power of kind of revisiting the sky, because things change. Stars get bright or blow up or disappear when they fade. So this was caught with the VLA not too long ago. So 2017, this was published. Actually published in 21, but the data in 2017. Here's another thing that wasn't there before, and now it is, a pulsar. So what we're looking at here, this is a host galaxy on the leftmost side back in 1998. Nothing at this location. In 2018, found it with the VLA, and then did some follow-up observations to get a sharper image. So what's going on here is this is a rapidly rotating neutron star. This is a core of a different star that blew up that's bright in the radio. And so we caught its birth. And that's, you think about the sky as this unchanging thing. We now understand that it changes a lot. It's actually rapidly changing if you look in the right way. Other science, so the VLA doesn't just do compact objects, it does wide angle work as well. Remember, the different configurations give you sensitivity to different scale on the sky. So what we're looking at here is actually the combination of the VLA and a large single dish radio telescope in Germany that's done a survey of a portion of the Milky Way galaxy. And it's detected previously hidden areas of star formation and also star death. And one of the things that's great about radio waves is they're large. The waves themselves are large compared to dust in the galaxy. And that's my whole hidden galaxies thing that I used to do, Dave. And now this is the similar kind of idea. But what we're looking at here is a portion of the Milky Way with this very sensitive survey And this supernova remnant, so this is the expanded remnant of an exploded star that wasn't known before, or this faint guy here wasn't known before. This is mapped very nicely, but it's also where high mass stars are being born. If you look at this in the optical, you don't get this kind of information because it's all kind of hidden in a very dusty region where the visible waves don't get out so easily. So it does this kind of work, and then also solar system. So here's an image of Uranus with the VLA. What you're looking at here, the different panels are maps at different wavelengths. So this goes from a short wavelength of 0.7 centimeters. The longest wavelength is 5 centimeters. And what we're looking at here is at the polar region. What was discovered here is a dark ring about 20 degrees away from the pole, and then a bright spot right up at the pole itself. I've read that this could be differences in temperatures or also elemental differences, but either way, it's thought to be that this difference in the image here is indicating a polar vortex of some sort that we get on Earth sometimes. So solar system. So, oh, and then this one, this is kind of hot off the presses. There isn't a paper associated with this yet. So this is really recent stuff I'm showing you. This is a fantastic project, a very big project, almost 2,000 hours with the VLA in all of the different configurations, A, B, C, and D. This image is ABC combination. And so what they're doing is they're looking at star formation and also indications of stellar death in some local group galaxies, 6 local group galaxies. It also maps the hydrogen between stars. And this one is just fantastic. This image, this galaxy rather, is called IC10. And we're seeing structure in it that we never saw before. This bubbles and holes, and then bright spots where stars are forming, and so and then the diffuse gas as well. So you're getting it all at once, right? Because you get all those configurations. So you get the fine scale structure and also the fuzzy stuff. And then what I want to point out is every dot in this image and these squiggly things are background radio galaxies. These aren't stars. These are background galaxies behind this nearby source. So this is a fantastic survey. The PI for this is Adam Leroy, and they're doing great work. And then finally, the VLA is very good at localizing explosions. So this is a project. There's an object called, well, it was one of a class called a fast radio burst. And these are kind of mysterious. They're very powerful things. They seem to be at cosmological distances, so very bright intrinsically. Not entirely sure what they are yet. This is a very hot topic of ongoing research. They may be highly magnetic cores of dead stars, or they could be signatures of collisions, but they get bright in the radio and then they trail off. And then in this case, this was discovered by a telescope in China, the FAST telescope, which is called the 500-meter aperture spherical telescope, but their resolution isn't very good. So follow-up done with the VLA narrows it down, and we see exactly where this thing is. So this is a hot topic right now. Not quite clear what they are, but they're cool. And so the VLA with the higher resolution is good at kind of localizing these things. Single dishes are good at finding them, and we can too, but single dishes are quite good at finding them, and then we're good at localizing them. So I want to make a plug. If you haven't been to the VLA yet, we are currently open, well, 7 days a week from 9 to 4. for self-guided walking tours. And we're now doing guided tours on every Saturday. It used to be every other Saturday, but that was too confusing. So we're doing them every Saturday now. So if you come out to the VLA on a Saturday, you get an expert guide to walk you around included. Just a couple things for closed Thanksgiving, Christmas, New Year's. And the gift shop right now, if you want to do holiday shopping, is open Monday to Friday. It will be open on the weekends soon. We're just kind of restaffing after the pandemic. It's taken a while. But and then I would mention we have a special event coming up on October 12th. We have an open house, which is a kind of a big deal. We have lots of tours, lots of talks. I'll be there. I'll give a talk. We have other talks going on. But I do want to give a plug, but that's not the end, Dave. If I can keep going, can I keep going? Oh, you're muted. Because I want
Please keep going.
Okay, good. All right, I want to give you a bonus telescope before I talk about the next generation VLA, because we run the National Radio Astronomy Observatory. That's the name of the organization that runs the VLA. We run a second telescope, which isn't so famous because you can't see it all at once. And that's called the Very Long Baseline Array. So this is bonus telescope. It's still run out of Socorro. That's where the headquarters is. But what the Very Long Baseline Array is, it works in the same theory as the VLA. We have individual antennas spread out, but they're spread way out. Each antenna, let me get you that. So here's an image, a picture of one of the antennas. This one's actually in Los Alamos. There are two antennas in New Mexico. Let me actually take that off so you can see the map again. So here's the Southwest US. There's two antennas in New Mexico, one in Arizona, one in Texas. What else do we have? We have California, Washington State. We've got Iowa, New Hampshire. And then we have an antenna in St. Croix in the Virgin Islands and an antenna out on the Big Island of Hawaii. Same kind of idea as the VLA. They're all 25-meter antennas. I think I mentioned Los Alamos, but I didn't mention Pie Town. The other antenna in New Mexico is in Pie Town. So they each measure electric fields. They're measuring voltages like the VLA antenna, and but what we do is a little different. We record the data at each antenna to disk, and then we actually ship them to New Mexico, and then do that combination of signals in Socorro, in the headquarters of the VLA. So the Domenici Science Operations Center is on the New Mexico Tech campus, and so what's cool about this is that these are very long baselines, and we have very unimaginative names, right? We have the Very Large Array, and this is the Very Long Baseline Array, because the longest baseline, the Hawaii to St. Croix baseline, is more than 8,600 kilometers. So remember, the resolution of the telescope depends on the separation of the antennas. So at this huge separation, we're talking about thousandths, milli-arc seconds. So extremely high resolution. Oops, did I go too far? No, we're good. And so just a couple of science highlights here about what you can get with very, very high resolution. This is such a neat result. So what we're looking at here, these images, the radio, here it is, this little inset here, that's what the VLBA data look like. And when it's embedded in these blobs, and I've got, these are two different galaxies, similar idea. The blue stuff is X-ray information, and the kind of reddish white, the reddish, if you will, is the radio. And so what's going on here is that these galaxies have supermassive black holes embedded in their cores, and they're shooting out jets of material that are changing directions. So radio, which is right down at the center, because this is an inset, it's right down in the center here, very, very, very small angle, is showing you the direction of the jets basically now. They're just a few light years long, so it's effectively now. But the holes in where the X-ray emission is, that's where the jets were in the past, and they cleared out big bubbles in the X-ray gas. So it's hot gas giving off the X-rays, and that's much farther out. So that's millions of light years. So in other words, we're seeing the change in the orientation of the jets of this black hole over time by combining the radio and the X-ray. And so this is another example of the power of multi-wavelength observations, right? You see these complementary views of these objects by using the different wavebands, because you're looking at, in this case, different material and showing kind of the evolutionary history of this thing. Another really cool result. So that was light years, right? So this is small. And only an astronomer would say that, right? That a light year is small. But on the scale of a galaxy, that's actually quite small. And here's another example of what I mean by that. So this is a different system. This is a VLBA observation of a galaxy. And can you see C1 and C2, the little blobs? The VLBA gives you very sharp images, but it tends to show you really small blobs. I mean, if you will. I mean, think about the VLA and A configuration showing you tiny structures. So the VLBA is even more like that. But what we're looking at here is the VLBA discovered 2 black holes in one galaxy. The separation here is about 24 light years. For a sense of scale, the distance between the sun and the next star is only about 4 light years. And these things are billions of times the mass of the sun. So very, very close together considering their size. Now this I love. So this was the subject of a press release. So this is real data. I'm showing you the real stuff. This is VLBA data. In the press release for this is the artist's conception of what's going on. But what you can see here is the image, the concept here is these 2 black holes. The VLBA is not sensitive to gas around the black holes, but it shows you like the relative separations compared to, they of course would be singularities down in the center here, but any material swirling around. So what we think is going on here is galaxies have black holes in the centers. That seems to be a universal thing. The Milky Way's got a supermassive black hole, some millions of solar masses. Big elliptical galaxy, some billions of solar masses. So it looks like this is likely a result of a merger of galaxies. Let me be a little mindful of the time and make sure, I'm going to skip that one because I want to make sure that we are still awake for the final topic here, which is the future. So the VLA and the VLBA are still cutting edge. I mean, they're still doing unique science on the planet, but they're aging. The VLA is over 40 years old now. The VLBA is about 30 years old now, amazingly. So we are planning a much larger facility and more flexible facility to actually replace both of them ultimately. And so what we are working on is the design for what's called the next generation very large array, NGVLA. Key points here is that the concept is that the array will have 10 times the sensitivity of the VLA. I've already, I can't, there's too much to talk about. ALMA is a telescope in South America that works at higher frequencies. I don't have time to talk about that, but that's a radio telescope that NRAO is involved in. Another day, we'll talk about that another day. But we need to build a telescope to make, kind of the big step forward. You don't want to like a factor of 2. We want to do a 10 times sensitivity improvement, 10 times higher resolution, wider frequency range. So instead of 1 to 50 gigahertz, 1 to 116 gigahertz. Here, there's in the bullets there, I'm listing a few, well, actually, so the key science projects, and I'll talk about the first two a little bit. I don't have time to talk about all of them, but it'll do some really neat science with 10 times the number of antennas of the VLA. So what this is an array that'll have 263 antennas, still centered near the VLA site. Most antennas will be in New Mexico, but let me show you, I'll show you a map of that in a minute, but let me show you a little bit about the science that it will be able to do. Now, I should say, this is in the design phase. We've been funded to do design, and that's continuing. And then we're building an antenna, and I'll show you a picture from today. But let me just show you a little bit about the science that it will be able to do that neither the VLA nor VLBA can do now. And that's about planet formation. So what you're looking at here is a protoplanetary system. This is real data with this ALMA telescope in South America. So what we're looking at here, the rings that you're seeing, especially if you look at the dark rings, this is a system where there's a young star forming in the middle, and there's a disk of material that we believe planets are forming out of. And these dark rings are where material in the disk are getting swept up and made into planets. But we're kind of surmising it, right? These gaps, we think there's planets forming in there because there's gaps where they're sweeping out, where the planets are sweeping up the dust. Now, to get a sense of scale, our solar system would be in this first ring. So up here, the inset up at the top, that's to give you a sense of the size of our solar system out to Neptune, right? And that would fit in this first ring. But what the NGVLA will be able to do is map that angle on the sky. So we would be able to see a solar system kind of system forming around a newly forming star out, in the Milky Way. And so what this is simulations of what the NGVLA will be able to do. If you looked at this system once every month, you can actually see planets forming in real time. We can make a movie of planet formation with the NGVLA, which is amazing, I think. I mean, that's just a stunning idea that we will be able to watch planet formation, catch it in real time. So that's one of the things that no other telescope on the planet will be able to do. One other science case I want to draw your attention to that it's going to be able to do with this frequency coverage, with this great frequency coverage, is rather than thinking about making an image, think about looking at the strength of radio emission over the range of frequencies. So this is known as a spectrum. So we can look at a radio spectrum. And so what we're looking at here is not radio data yet, but what this is showing, is the signatures in frequency of 3 different prebiotic molecules, and where they are predicted to emit in the radio frequency. You see the different lines. It looks like a thicket of lines, right? There's a black, a red, and a green, and it corresponds to the 3 different prebiotic molecules in the wave band of the NGVLA. It's actually right now in the wave band of the VLA, but the VLA is not sensitive enough. It can't see that, but the NGVLA will be sensitive enough to detect these molecules. And this is kind of exciting because these prebiotic molecules, I mean, it'd be very interesting to know if you look at a lot of star forming regions, how common are they, right? Do a lot of protoplanetary systems have these sort of building blocks of life? So that's an interesting project. Are they rare? Are they common? Be an interesting thing to be able to say for sure. So where are we in the planning? So it's underway, but let me show you where this telescope would be. So a bunch of different maps here. Let's focus in on New Mexico. So on the left here, here's the state of New Mexico. The current VLA site is down here. This is the plains of San Agustin. We would intend to put the core of this array very close to the current VLA. and then have spiral arms, if you will, of antennas coming out from that. You can kind of zoom in and see what the core would look like here. Lots and lots of antennas in the middle, and then they get sparser, and then they spread out through the Southwest US and then across the United States, actually where the current VLBA dishes are, with some changes. This is draft. We're still playing with the array configuration, because where the antennas are change how, what the response looks like and so on. So this is part of the design work that we're doing. So this isn't finalized yet. But the key thing to note, so 263 antennas, most of them in New Mexico, nearly 200 of them in New Mexico. Now, each antenna will be a little smaller than a current VLA antenna, and frankly, a more modern design. So this slide, this is actually my last slide, shows you, this is a model of what each antenna will look like. So the antennas, most of them will be 18 meters versus 25. And then a small number of them will be very small, like six meters across, so you can pack them close together. But most of the 263 antennas will be this 18-meter design. So this is the prototype antenna that we're building. So CAD drawing, so this is the engineering, the company is called MTEX, is building this prototype. And then the picture here is real from today. So we have a webcam. If you Google NGVLA webcam, that's all you need to do. If you Google NGVLA webcam, you can link to our live webcam to show you the progress of the construction of the prototype antenna. So this is what it looked like today. It's just next to the VLA control building. You can see VLA antennas observing back here. This is the east arm, part of the east arm. And then this is a construction site. And you can see taking shape now this backing structure, the lattice. What you're looking at here in the CAD drawing is looking at it from behind. So this is the support structure, and then the smooth panels will be on the other side. And so what you got here is it's coming into shape. And so that's happening. And then this is going to be this subreflector. So very exciting. The prototype antenna is taking form. We need to test it very well. So what's going to happen, and when you go out to the VLA and visit, you can stand up on our balcony and look out over this construction site and see it taking shape. And again, you can also look at the webcam. So we need to test the antenna very, very well, because it goes to higher frequency. It has to be smoother. It has to point very well, because it's going to be dealing with small wavelengths. It's a kind of a different design from the older VLA antennas. And so we need to test that very thoroughly. So for the next year or so, it will come into shape. We'll test it on its own to make sure it meets spec. And then we can plug it into the VLA. There is enough capacity in the correlator, in the computer, and we have a fiber optic connection from this test pad into the control building, and so it can act as antenna number 28, and we can test it in the array. So we'll be doing that. So the timeline. So this is very exciting. This is happening now. We're still working on a design for the array and the data systems. It's a big data problem. It's a lot of data going to come from 263 antennas. So we're working on that. We do not yet have funding for construction. We need to complete the design before we go after that. We have been endorsed by the National Academy of Sciences, the decadal review for astronomy and astrophysics. That doesn't come with a check, but it allows us to go after money. So if all goes according to plan, we work on this antenna for a while. We would hope to start construction later in the decade. Early science would start, turn of the decade, early next decade. Full science well into next decade. It's a big project. It's a big project. Lots of hurdles to jump through, but it's going well and exciting. So I think I'll do this. I'll say thank you and see
Oh,
if there are
righty.
further questions.
Well, I've got a question.
Sure.
So is the Domenici Center still going to be part of the NG VLA, or is it the project so big that you're going to have another regional center in Albuquerque, or what's the plan for that?
Yeah, still a TBD, but one thing we do know is, in fact, let me go back to the map. So it is big, and so there will be more of a kind of distributed model, most likely. So for instance, right now at the VLA, we've got about 65 people who work out there to do all the repairs and maintenance and so on. We may want to move that maintenance center to not be right at the core of the array, because we make our own radio frequency interference there. So we envision like a maintenance center, which could be not determined yet, but one could imagine it and say Magdalena, potentially shift it out, possibly, again, could float. The Array Operations Center, that could be in Socorro. That kind of makes sense, right? Now, you don't want to be so far away. But the Science Center, if you want to have more visiting PhD scientists, it doesn't have to be at the Array Operations Center. That could be in a larger metropolitan area, maybe Albuquerque. So these things are not determined yet, Dave. There will be a distributed model, right? The Array Operations Center, the Maintenance Center, the Science Center, the Data Center, where will the Data Center be? They don't all have to be right in the exact same place, but you know, some geographical distribution is likely, but that's TBD. That's part of the design.
Okay.
So I have a question.
Yeah.
You mentioned the correlator, and I'm imagining that is to take the data from all the different antenna and merge them. Is that correct?
That's correct.
Okay. And so the data you receive then, does that go for processing through any sort of other computer systems? And if it does, does it take much computing power? Has there been an increase in computing power that has helped you get data sooner or with finer resolution?
Yeah, so for the current VLA, that correlator was part of this upgrade about a decade ago, and that allows us to have wider bandwidths, so a finer frequency resolution. We call them channels. So we have more channels over a wider range, and so yes, that we can do science now that we couldn't do 20 years ago, even though it's the same antennas, but we needed that more powerful computer. Now for the NGVLA, oh, and I haven't done the math, but you guys can do the math. So think about the number of baselines. So what we do is we compare pairs of antennas. So for the VLA, we have 27 antennas. So how many independent baselines are there with 27 antennas? Well, it's 27 times 26 divided by 2. Is the number of independent baselines. So for the VLA, at any moment, you've got 351 baselines, right? I actually haven't done this. What is it for 263?
We're computing the computational needs right now.
There you go.
Somebody is.
I see Dave working.
252?
How much?
It's 252 things, 2 at a time, right?
So yeah, let's say 263. Yeah, so 263. And let's never mind let's call it 250, because there are some some of them will act together.
Wow, for
250.
252, comes out to 31, almost 32,000.
Yeah, right, exactly. So
Okay.
big and wider frequency, right, as well. So you've got wider bandwidth coverage too. So here's a number. The average compute capacity required, not tomorrow, but by the middle of next decade, is about 60 petaflops per second. It's enormous. It's enormous. Yes, it's huge. Now, fortunately, we don't need that tomorrow. We don't need that. It'll grow in phases. But yes, it's a big data problem. So in some sense, the NGVLA, we know how to do it, right? We know how to build radio interferometers. We've been doing it for a long time. And part of it is easier. I didn't mention this, but there are so many antennas that we won't reconfigure. They will just be parked and we don't have to move them because we've got so many different kinds of baselines. But the data handling is an exciting and fun problem. I'll put it that way.
Okay. Looks like Tish Morris had a question. Are the VLBA antennas on the same Y alignment, extended out the same lines as the original VLA antennas?
Good question. No, they're not. It's kind of more random. They're not. They don't line up with the VLA. They're scattered around, more random. There's more. Let's put it this way. They are further apart east-west than they are north-south, because in east-west, the longest baseline is the Virgin Islands in the Caribbean to Hawaii, and north-south, you've got Arizona, you got Texas on the south, and the northern ones are in Washington State and in New Hampshire. So it's kind of more of a random distribution, but not on the Y of the VLA. I can stop share if people
It
want.
looks like Randy has a question.
Huh?
Hi, the red dots representing these radio type arms, what's the restriction on where those are placed? How much, because you're on a very different geography scale.
Yep. It's actually pretty flexible. They can move around some and not affect the response of the telescope too much, which is good because that means that, so, okay, let's focus in on the core. That we have some control over. Well, we do have control over that because that's really right next to the VLA. That's the idea on the plains of San Agustin. So we can place those. The ones that are farther out, the red dots that go farther out, we have some flexibility. And the rule of thumb is you can move antennas around to about 10% of their baseline length and not have it affect it too much, which is good because then that gives us flexibility of where we place the antennas, because we don't want to place them in any sensitive places, right? We don't want to place them on land which is maybe where you don't want to put an antenna, either for sociological or for geological reasons or whatever. So we got some play there, which is good. So we can move that around, and so that's
What
part
was
of why. Sorry, go ahead.
You
What was
said about 10% of baseline? What is
Yeah.
that?
So in other words, so think about, if you can see my cursor, imagine the core. All right, let's say, where do I want to put, say, this antenna down here in Mexico? Does it have to be exactly in that spot? No, it could be in a region anywhere, which is, say, 10%, a radius of 10% of the distance between it and the core.
Oh, okay, good.
That's what I mean. So it can wiggle around a fair amount, which is good, because you don't want to put it in the middle of a stream, and you don't want to put it in the middle, you certainly don't want to put it in the middle of a town. So there's flexibility there.
Okay, good.
Excellent. I've got a question. You said there's no charge to the scientist or public to get the data. Are they required to share the data? And if so, do they get like a couple years to keep those cards close to their PI's face and then release it? Or how does that work?
They get 12 months. So there is a proprietary period of 12 months after the end of your observation, where you've got the data to try to get that reduced, to get your students going, to protect their work, to get that reduced in your paper out, and then it becomes public. So all the data sit in our archive in Socorro until, well, it sits in the archive, and the PI has private rights to it for 1 year.
Okay. I had one more question. I think Corona Borealis is there's supposed to be a sort of periodic supernova that's going to go off.
Nova, yeah.
Are there plans to observe that?
You know, that's a fine question. We just accepted proposals. What is this? This is the 18th of September, right? Yes.
Yeah.
So we just accepted proposals, and our science panels are reviewing proposals right now. And then they're going to meet in a couple of weeks to make the final suggestion to us. So I have not buzzed through the titles of the proposals yet, but we'll see if somebody on the planet has proposed to do that, because it seems, yeah, we should. So
And wasn't that supposed to go off by September?
any day now.
Any day. Okay.
Any day. These are astronomical timescales. So any day now. But I'm rooting for Betelgeuse to blow up before I die. That's what I'm hoping.
There you go.
So do you accept proposals from children?
Well, the children would have to understand radio interferometers pretty well. So anybody can apply, but it's going to be competed, and that also is a technical competition. You have to propose a project and explain exactly how you're going to do it. So yes, we don't have an age limit. We don't have an age limit. We do not have a country limit. We don't have an institution limit. You don't have to be at any particular kind of institution. Anybody can apply. So a smart kid who goes through and understands the technical needs of the proposal. But actually, we have had so children. I wouldn't say, well, yeah. How do you define child? To me, that's anyone younger than 40 now. But we have had classes, write a proposal. I think the professor helps with that. But we do observation. If it's good science and the panel recommends it, then we'll try to do it. I would say, let me, to be on the telescope. Yeah, I'll just leave it there. I think that's a complete enough. More detail.
Are you planning to use Arecibo again?
Arecibo, sadly, no. Arecibo is done. Arecibo fell down.
It collapsed, yeah.
Right.
It
Right,
collapsed.
exactly.
What's that?
Right, you have some infrastructure still there. I was just wondering if the site was usable at all.
That's a great question. That's actually a different organization. And so that isn't the National Radio Astronomy Observatory, but my understanding is that the visitor center is still open and doing a lot of great programming. And so, what happens, are there other radio telescopes? They'd have to be brand new radio telescopes built there. That's a possibility. Certainly wouldn't rule it out, because you're right, there is infrastructure there. But right now they have they've got a great visitor center and very active educational programming there. So I'd say that's on the table, but nothing determined.
This might be a dumb question, but years ago, the Hubble telescope did this so-called deep field experiment where they picked a tiny little patch of sky that was out, I don't know, in the middle of Orion or something. Would it be possible at all to point the VLA towards that little patch of sky?
Yes, and we have that, and there's also a similar kind of field in the southern hemisphere. Yeah, and so you see the radio galaxies that are in there. I'm not going to be able to find an image in enough real time here, but yes, and we have. That's a kind of project where you just kind of dwell on the sky for a very long time. But that's that. What's that? Oh,
Oh, okay.
all right.
Can you put up the information about October 12th again?
Oh, yes. Well, actually, if you Google visit the VLA,
Uh-huh.
I could do
What
that.
is this called?
This is-
Annual thing or
This is
Open
called
house?
the open house.
open
Yeah,
house?
yeah. Yep. And we'll have multiple tours. We'll have scientists and engineers. We'll have an engineer stationed out at the barn, the barn, that big structure where we do the overhauls for the antennas. We affectionately call the barn. And so there'll be somebody out there explaining about what we do there. We'll have folks stationed, all over the array, and then we'll have these walking tours. You'll be able to see the NGVLA prototype being constructed. There'll be 3 different talks that cycle through the day. And to be honest with you, I don't know what the other 2 are. I'll be talking, actually, it'll be a lot like this presentation. So you will have seen it already. But I'll be out there meeting and greeting folks. We'll have food trucks. That's always very exciting for the staff because generally there's no food out at the VLA. But the last couple of open houses, we've got food trucks, and it's mostly it's a lot of staff out there eating. So that's you'll see us out there.
That's great.
Is there a food truck from Pytown?
Oh, I would. Yeah, we don't. There's a couple of different food trucks. One from Wandering Scorpion. Socorro folks might know the Wandering Scorpion, and
Yeah.
Red Wagon Coffee will be out there. And we also get a food truck from the Alamo Navajo chapter comes out. And so we'll see who's out there today. But I learned my lesson the hard way. Fortunately, I wasn't giving a talk, but I had one of those cowboy coffees, which was coffee and espresso added from Red Wagon. Oh boy, I was kind of jittering the whole day. So I'll make sure I don't do that again, particularly before I give my talk. Or it'll be over in 10 minutes.
Okay. Any last questions?
How much of a problem is contamination from terrestrial sources of radio frequency? Is that a big problem for you guys?
Yeah, it's something we're working on. So there's 2 things to think about there. So the reason the VLA is in such a great site, and we want to put the core of the NGVLA there, is that it's flat where the core will be, right? And then it's ringed by mountains. And so the mountains do what we call terrain shielding. So we don't have a direct line of sight to say Sandia Crest, which is a strong radio antenna source, right? So that's good for the truly terrestrial stuff. And then you'll see signs all over when you go visit the VLA. It says, please turn off your cell phone. Please turn off Bluetooth. Anything that radiates, please turn it off, right? But our biggest problem these days is actually satellites. GPS satellites are very strong where in parts of where we observe, and there's just more and more. You heard about these fleets of satellites.
Starlink?
Starlink, right? So Starlink is a great example, and we're working closely with SpaceX to learn how to share. So right now, we're doing experiments with them where they avoid the VLA. So what we don't want is transmission straight down the bore site into one of our antennas. That's bad. And so what we do is we share information with them about where we're pointing and at what frequencies. And so far it's quite promising actually that they can avoid where we are. We avoid looking right up at a satellite. And they're at this point, kind of not beaming with a cutout for the VLA, which is good news. The other thing that we've noticed is that we can detect them, of course, but it's very baseline dependent. So they'll pop up on one baseline and then go away and pop up on another one and so on. So anyway, yes, it's a concern because there's going to be a lot of these, and we are proactively working with these folks, partially because so there are some slices of the spectrum that are only for radio astronomy, and nobody else can be in that part of the spectrum, but it's actually a small fraction of what we actually observe. So in the L band, for instance, near 1.4 gigahertz, there's a cutout specifically for radio astronomy, but most of our band is not protected in that way. So we need to learn to coexist, and so far it's promising. We seem to be able to deal with that, and what we're hoping is to set up these processes with SpaceX that then other providers will adopt. I will say that one thing that we are more worried about is this concept of the direct of this, when you're on your cell phone, what you're actually talking to is a cell tower some kilometers away generally, right? But there is this concept of cell coverage directly from satellites, and that concerns us. So we're more worried about the satellites than what's on the ground, although we worry about everything.
Do you have some sort of arrangement with, say, the Air Force or other aerial people to prevent overflight of, say, aircraft with mapping capability?
Yeah, we can't. So we actually, excuse me, we don't own the space above us.
Okay. No
So
exclusion on aeronautical charts.
that's right. We just ask that aircraft, we don't want any drones, please, no drones coming to visit the VLA. Drones are bad. But we ask that no aircraft come within 500 feet of an antenna. Yeah, that's close. But yeah, I mean, the aircraft pass over us all the time. We do have some radio frequency interference. We just have to cut it out of the data. But generally, again, you have different responses on different baselines. But yeah, RFI is just a fact of life for us. We have algorithms. I mean, the data are lost, right? If it's real bright, we can cut it out of the data. We can't reconstruct the astronomical data. But yeah, we've been dealing with it. We're in the world, and we don't own all that spectrum.
Very good. Okay. Well, thanks so much, Trish. That was a delightful talk.
Thank you.
And we'll put it on YouTube. I'll send you the link. You can show your friends and colleagues and whatnot. Next month, we have David Weinberg talking about the mysteries of medical science. So looking forward to that on October 9th. And so thanks everybody for coming. Thanks so much, Trish. That was a fascinating presentation. Okay. All right. Take care, everyone. Live long and prosper.
Bye-bye.
Take care.